Today we will see the answers to the assignment 5. I hope you have solved it correctly, and many of the questions were very easy. So, let us look at the questions and corresponding answers. The first question, a little bit elaborate, but this is related to that diversity of two antennas when rain is occurring and you have loss due to rain fade, and you put another antenna, another receive station a little far away, and using both of them together you get certain gain. Now, this is related to that. Here a lot of figures are given, and a station receiving at 20 gigahertz from a satellite at 20 degree elevation has link availability of 19.9% and it experiences 11.31 dB attenuation during day. Now, this is a single site attenuation. What will be the diversity gain in dB when a diversity station, another station is added at a distance of 10 km with a baseline orientation angle of 85 degrees to the satellite. As we have been given what is the frequency, there is 20 gigahertz, elevation angle 20 degree, and the single site attenuation 11.31, and then there is a distance between two sites at 10 km, and baseline orientation angle to the satellite is 85 degree. So, let us see how ITU model tries to solve it. This site diversity advantage depends on distance, in this case 10 km, operating frequency, elevation angle, baseline operation angle. These are given by ITU model, and each of them gives a different gain, and that has to be multiplied together to get the total advantage. So, gain due to separation distance, which is 10 km, which is GD, this D is the distance and A is single site attenuation, which is depends on two coefficients A and B, A into 1 minus e to the power minus B D, this D is distance, where A is defined in terms of single site attenuation as A equal to 0.78 AS minus 1.94 into 1 minus e to the power minus 0.011 AS, and in B is given by 0.59 into 1 minus e to the power minus 0.1 AS. So, first we have to calculate this A, and where AS is already given, B where A is already given, and then we try to calculate the gain due to distance separation, where the D term will come into picture. Let us see what are the other gains ITU says. It says gain due to operating frequency is GF, as depends on frequency, is e to the power minus 0.025 f, and this f is in gigahertz. In our case f is already given. Then other gain is due to elevation angle to the satellite, that is GE theta, theta is the elevation angle 1 plus 0.006 theta. The other one is the baseline orientation angle G phi, that is function of phi 1 plus 0.002 phi. The baseline is between two stations, you draw a line, and when the two stations are looking toward the satellite, the azimuth angle towards the satellite, that is called phi. Okay. So, we have 4 different types of G, and the total gain, total diversity gain will be GD, GF, G theta and G phi. All the expressions are already given. So, if we put all these expression and corresponding values which are given already, we will first find out A, where 11.31 is the single site attenuation which is given, and here also 11.31. So, A comes out to be 7.44, B similarly 11.31 single site attenuation is given. So, B comes out to be 0.4, and the gain due to distance is depends on this A, and here e to the power minus 0.4, which is the B, multiplied by the 10 kilometer is the distance. So, GD comes out to be 7.3. Others are much simpler. The frequency was 20 gigahertz given, F is supposed to be in gigahertz. So, e to the power 0.025 minus 0.025 into 20, which comes out to be 0.61. Elevation angle G theta, again 20 degree is given. So, it comes out to be 1.12, and baseline orientation 85 degree is given. So, G phi comes out to be 1.17. So, all of them multiplied together we get 5.84 dB. This is the I2 model. Okay, and 5.54 dB is our option B. So, choice is B. Let us go to the second question. This is very simple. What is meant by f in direct method of G by T measurement using Y factor, which is expressed as G by T is equal to y minus 1 8 pi k divided by f lambda square. This expression you have come across when we try to do a G by T measurement using direct power measurement from the radio star. Now, this f stands for the let us see the options which are given. F is a noise figure, flux density of radio star or failure rate, all stands for f, and none of this, but obviously it is a radio star based measurement. So, f is a flux density of the radio star. So, f represents the flux density received from the radio stars. So, appropriate option is B. Let us see the third question. For a given oscillation d by lambda, d is the diameter of the parabolic antenna and lambda is the wavelength of operation. D by lambda is 75 for that oscillation. As per ITU mask for oscillation reference antenna radiation, the gain g theta in dB at a theta degree away from the peak gain will be, there are various 4 options are given 29, 30, 31, 32 etc. You remember I said that ITU has given a mask for antenna radiation pattern from the ground, so that radiation does not take too much of geosynchronous geostationary arc, so that we can place the satellite at a distance away. So, to limit the interference they have given a mask. So, that mask is g theta here. So, as you go away from the peak gain, as you go away g theta, that should fall, the gain should fall. Here the d by lambda is 75, which is given. Theta, if you remember, theta is the 3 dB beamwidth. If you remember, we calculated 75 lambda by d, which is 75 by d by lambda, which is in this case 75 by 75, which is 1 degree. So, 1 degree away from the peak, that is what we found out. Now, as per ITU recommendation mask for the reference antenna gain at theta degree will be, this is the mask which is given, g theta is equal to 32 minus 25 log theta, and this is valid for d by lambda equal to or greater than 50. In our case it is greater than 50, in our case given is 75. So, we will use this expression. So, in this case theta is already found out. So, we put the values g theta, theta is equal to 1 degree, 32 minus 25 log theta, in case of theta I put 1. So, this term goes to 0. So, we get 32 dB, which means the correct answer is D. Now, let us see another one. A VSAT network is allotted 42 dBW in a linearized transponder. Now, a network will have many VSATs and of course, hub. The network will operate with 2 carriers from the hub to support many VSAT carriers. That is their own arrangement, that one carrier is not able to support for their own reason. So, they have put 2 carriers to support VSATs. 2 hub carriers need 36 dBW each. So, each of the hub carrier needs 36 dBW. So, there are 2 hub carriers which draws from the satellite 36 dBW out of 42 dBW which is allotted, and each VSAT carrier needs 26 dBW, 10 dB lower than the hub carrier. How many VSAT carriers can be accommodated in the transponder? You try to understand that it is you have to go into power and how much power out of the total power which is available for this network, how much power is taken by hub carriers, and then rest of the power has to be distributed with all of them are equal, distributed with 26 dBW carriers. So, how many such carriers can support rest of the power, can be supported by the rest of the power. Options given are various options 20, 17, 21, 19 like that. So, let us see how do you calculate. VSAT network is allotted 42 dBW from the transponder. Do not worry about the back off etc. operating point, they are allotted. So, the transponder operator itself they know what backoff has to be given, etc., they have already allotted 42 dBW, so that you can operate, and this is only power, bandwidth is not given here. So, each hub carrier takes 36 dBW power and the network has 2 hub carriers. So, 36 dBW, 2 of them 3 dB more. So, it becomes 39 dBW which hub carriers will take together. It is solved this way, hence the power consumed by the 2 hub carriers is 10 log 2 into 10 to the power 3.6, and then it comes out to be 39 dBW. So, 42 dBW was the total power. Out of that 39 dBW is taken by the hub carriers, and each VSAR carrier needs 26 dBW. So, you convert 42 dBW into ratio power, that is wattage, 39 dBW in terms of wattage, and subtract these two. So, that much power is allotted to this 26 dBW you convert into watt. So, divide by these two. So, assume one can accommodate n number of carriers, VSAT carriers. So, n is equal to, you can express this difference, and the each individual carrier of VSAT, all of them are now converted into watt. So, it comes out to 19.85 carriers. Now, 0.85 carriers we cannot transmit, we cannot accommodate any fractional number of carriers. So, therefore, if you remember in the class already we said that it has to be the lower integer. So, the maximum number of carriers can be accommodated is 19 full, that is the correct answer, correct choice is D. Okay, let us go to the next question. Now, this is simple. Why most of the VSAT antennas use offset feed mount? You try to recollect the diagram, and what is offset feed mount? Normally a parabola, and the focus of the parabola you have a feed, and but in the VSAT, in the bank ATM and many other your DTH, you will see that parabola and feed is not coming at the focus, it's slightly offset. Now, the reason it is asked to maintain the balance of the antenna setup, to increase the efficiency of the antenna above 80%, to minimize the signal blockage, or none of these. Now, if you recollect that if you put the feed in front of the parabola just at the focus, prime focus feed, the signal is blocked. So, that is to avoid the signal blockage, only one portion of the parabola is taken which is not coming where the feed is not coming in front of it. So, that is why it is called offset. You try to recollect the diagram. So, offset feed is used to reduce the blockage of the received signal, that is the correct option, that is the choice C. Now, let us go to another question. A satellite link in clear sky uses using 8 phase PSK modulation scheme. It is needed to change the modulation scheme to counter the rain fade. So, when rain occurs, there will be fade, and by adaptive modulation and adaptive coding you can get certain advantage, if you remember we discussed in the class. So, here this is a question that you are using 8 phase PSK, and which modulation will give you certain rain fade advantage. Is it BPSK, 16 phase PSK, 32 PSK, or 64 PSK? You can see that 8 phase PSK BPSK is lower than 8 phase PSK, and 16, 32, 64 PSK all are higher than 8 phase PSK. Let us see the reasoning. The number of constellation points in a modulation scheme directly affect the average power required by a modulation technique. Number of points in IQ constellation, if you recollect. Higher number of signal points in the constellation diagram demands higher power. So, reduction in number of signal points in a modulation scheme helps this power reduction. So, the rain fade can be countered by reducing the number of signal points in a modulation scheme. So, from the given options, only BPSK has less number of constellation points than 8 phase PSK. As you go on increasing this n number, or M you call MPSK, your constellation points are increasing. So, therefore, the appropriate option is A, because A is the only one option given which has less than less M. So, less number of constellation points. Now, next question. To improve the single site attenuation of 10.31 dB at annual link availability of 99.9%, a second site is added to get a diversity gain of 5.84 dB. what is the joint site rain attenuation for the same link availability. There are 3 parameters coming. Of course, there is at a particular probability you have a single site attenuation. Now, when you add another site, it will have a joint site rain attenuation. So, what is the advantage from the single to the joint site rain attenuation? That advantage is given, that is diversity gain is given. So, diversity gain is given and single site attenuation is given. You have to find out the joint rain attenuation, joint site rain attenuation. The options are given, 4 different options are given: 3.56, 4.47, 5.78, 9.40 dB. Now, the diversity gain GD can be expressed as single site attenuation with a particular probability minus joint site attenuation with the same probability, and ASP is a single site attenuation at probability level P, and AJP ASP single site, AJP is joint site attenuation probability level P. So, by using the same formula where your AS is given, GD is given, you have to find out AJ. AJ comes out to be 4.47 at 99.99% reliability. Okay. Hence, the appropriate option is B. Right. Now, let us go to the another one. Using radio star based G by T measurement, where F is radio star flux density. In earlier one of the question we discovered that F is the radio star flux density. AE is the antenna effective aperture and F is the frequency. The noise power ratio Y is given as, there are 4 different options given where FAE and 2 KTS are directly ratioed, 1 plus them, 1 minus them, 1 plus 2 times them, like that, 2/3 of them, like that. 4 different options are given. Try to recollect the radio star based G by T measurement, where we used a power ratio of looking at the radio star and looking at the cold sky. In Y factor based direct G by T measurement, the ratio of measured powers at receiver output, that is Y, is P when antenna is towards the radio star divided by P antenna towards the cold sky. This P stands for power. Okay. Now, when a P this power is measured, that is radio star flux density power coming, antenna effective aperture is taking that power, that is the radio noise, I could say, and then receiver noise KTB comes into picture, and then together you measure, that is the total power. Whereas, when you look at the cold sky, assuming that is negligible temperature coming from the sky, so it is only the receiver noise temperature. So, if you remember that radio star is random polarization, you do not know which polarization is coming. So, we take a factor 0.5 and F is the flux density from the radio star, AE is the antenna effective aperture, B is the bandwidth, and that is coming from the radio star, and KTSB is generated by the receiver, where TS is the system noise temperature of the receiver, K is the Boltzmann constant, that is the P antenna towards the radio star. And when it is going to cold sky, the first part is not there because assuming cold sky is giving almost negligible noise flux power. So, it is only KTSB receiver noise power. So, if you divide these two, you can see B gets cancelled, and then KTS TSB this is 1, and then this is 0.5. So, denominator goes to 2. We have KTS, B gets cancelled, and in numerator we have FAE. So, it is 1 plus FAE by 2 KTS, and that was one of our option. That was the appropriate one is B option. Okay. So, these are simple, but you have to recollect the understanding of it. So, similarly, the last one the last but one, that is a 9th question. A station transmit power amplifier output is monitored through a 20 dB coupler. When a power meter shows 1 watt power at the coupler output, what was the power amplifier output in dBW, which is given to the coupler. So, if you remember here your EIRP measurement, I said that the EIRP was power transmitted by multiplied by the transmit antenna gain. Here power transmitted, how do you measure? Because it is normally high power. So, if you continuously when you are transmitting, that time you pick up some power which is used through which is picked up through a coupler. Now, a 20 dB coupler will take the power out of that, a fraction of the power which is going will be taken out. So, here and that power which is measured is 1 watt at a particular time, but the coupler definition is a 20 dB coupler. 20 dB below the power whatever being transmitted is taken out. So, what was the power amplifier in dBW? So, here somewhere watt is given, careful. So, options given, that is power amplifier output options given 19, 20, 21, 22. So, let us see. Assume power output of power amplifier is P watt, and in 20 dB coupler the output will be 100th 20 dB if you can dB converted to ratio. So, 100 times of the input power is coupled out, which is P by 100 watt, and which is measured as 1 watt. So, P by 100 is 1 watt, then P is 100 watt, and answer is asked in dBW. So, we convert 100 watt into dBW, which is 20 dBW. So, your correct option is B. Now, we have the last one. This is from memory you have to recollect, that is ITU recommends that ground station antenna side lobes. It is similar to the ITU main peak gain mask, radiation mask. Here the side lobe part is defined, that for theta equal to 1 degree to 20 degree, theta is away from the peak gain, the angle away from the peak gain, 1 degree to 20 degree, and for d by lambda greater than 50 should be restricted such that 90% of the side lobe peaks, so many side lobe peaks that will come, 90% of them, if you sum them up, should not exceed this relation, is the relations given g theta 32 minus 25 log theta, 31 minus 25 log theta, 30 minus 25 log theta, 29 minus 25 log. You have to recollect which was recommended by ITU, and ITU recommends the option D, which is 29 minus 25 log theta. So, with this assignment 5, all the questions are answered. Thank you very much.